In Chapter 2, we'll be reviewing some basic principles of chemistry. If chemistry is brand new to you, you might find this a little bit overwhelming, and you may need to spend some extra time gaining an understanding of the material in this chapter. We'll begin by looking at atoms. Any substance in the universe has mass and occupies space and is defined as matter. And all matter is composed of extremely small particles called atoms. Understanding the structure of these atoms is going to be critical to our understanding of the nature of biological molecules. Atoms are composed of three basic components: protons, neutrons, and electrons. Protons are positively charged particles, and they're located in the nucleus. Here you can see two examples, one of hydrogen and one of oxygen. Hydrogen has only one proton. Oxygen, however, has 8 protons. Neutrons are the other particle that are located in the nucleus. Neutrons are neutral particles, that is, they have no charge. You can see here that hydrogen does not have a neutron, so it's sort of an exception. Oxygen, however, has 8 neutrons. In general, an atom will have an equal number of protons and equal number of neutrons. Finally, there are electrons. In oxygen, we also see 8 electrons. Now, electrons are negatively charged particles. This is why an atom usually has just as many protons, positively charged particles, as electrons, which are negatively charged. The electrons, however, are found orbiting around the nucleus in structures we call orbitals that we'll take a closer look at soon. So oxygen has 8 protons, 8 neutrons, and 8 electrons. Hydrogen has no neutrons, but because it has 1 proton, it also has 1 electron in its non-reactive state. So when we have an equal number of protons and equal number of electrons, the atoms are electrically neutral. It's the number of protons that defines the element. The number of protons tells us the atomic number of the atom. Every atom of a particular element has the same number of protons. That is, oxygen will always have 8 protons, and anything that has 8 protons is oxygen. Now, a number of atoms of the same substance is an element. So an element is any substance that can't be broken down into any other substance by normal chemical means. It's purely one kind of atom. This is a picture you're all probably very familiar with. It's the periodic table of the elements. And we can see the atomic number of each one of the elements noted here in the table. This table doesn't include atomic masses. Many tables will include an atomic mass below, which is essentially double the atomic number, because protons and neutrons are almost equal in weight. So anything with 1 proton is called hydrogen, and anything with 11 protons is called sodium. In green, you see the primary biological elements. Let's take a quick review of mass versus weight. Mass refers to the amount of a substance, whereas weight refers to the force of gravity that's exerted on the substance. So mass, whether we're on Earth or on the moon, will be the same no matter what. However, weight would be different. My weight on Earth is much heavier than my weight on the moon, because the moon has 1/6 of the gravity of Earth. So each proton and each neutron has essentially the same mass, which is approximately 1 Dalton. Daltons are very, very small units of mass. To give you an idea of how small, it takes 602 million billion, that is 6.02 times 10 to the 23, Daltons to make 1 gram. So protons and neutrons, although they have mass, are very, very light. And electrons have 1/1840th of a Dalton for their mass. So their contribution to atomic mass is negligible. So we say the sum of protons and the neutrons is the atomic mass, which is generally double the atomic number. So electrons are the negatively charged particles. Electrons are maintained in their orbitals by their attraction to the positively charged nucleus. When an atom has an unequal number of protons and electrons, it's unbalanced and considered an ion. Cations are atoms that have more protons than electrons, and thus they have a net positive charge because they have more protons which are positively charged. An anion has fewer protons than electrons, and thus they have a net negative charge. Sometimes atoms of a single element possess different numbers of neutrons. These are considered to be isotopes. Although over 99% of the carbon on Earth is carbon-12, that is, it has 6 neutrons and 6 protons. That is, it has 6 neutrons and 6 protons. The other 1% is composed of some isotopes, those that have different numbers of neutrons than they do protons. Carbon-13 thus has 6 protons because it's carbon, and the protons define what the element is. And carbon-14 has 8 neutrons. 6 plus 8 is 14. Definitely, it still has 6 protons because it's carbon. Now, carbon-14 is a radioactive isotope. That means it's unstable and it emits radiation as the nucleus breaks up into elements that have lower atomic numbers. The half-life is the time that it takes for 1/2 of the atoms in a sample to decay. We often use this radioactive isotope, carbon-14, in carbon dating. And it works like this. The half-life of carbon-14 is 5,730 years. So if we had 1 gram of carbon today, in 5,730 years, we would have 1/2 a gram of carbon. So by determining the ratios of the different isotopes of carbon, that is carbon-12 to carbon-14, over time, any compound that contains carbon will have less proportionate amount of carbon-14 because it decays into another element over time. So electrons are the key to the chemical behavior of an atom. So we need to explore the number and arrangement of electrons in their orbitals. In the Bohr model, we see that electrons have discrete orbits. This is the Bohr model. Modern physics defines an orbital as the area around a nucleus where the electron is most likely to be found. And no orbital can contain more than 2 electrons. Now, the orbitals are not to be confused with energy levels. We'll discuss those here in a moment. But there are 2 types of orbital. There are spherical orbitals that look like this, in which the electron spends an equal amount of time in every single point in this sphere around the nucleus of the atom. And then there are p orbitals, which have more of a dumbbell shape. So the electrons move in their pair most of the time in any other region covered by purple around the region of the nucleus, with the nucleus being right here in the middle. Now there are 3 p orbitals. When we put these 4 different orbitals together, we have a full electron shell. That is 8 electrons, 2 in this spherical one, 2 in each of these p orbitals that are in different orientations around the nucleus. This is the best summary of how each of those orbitals comes together to form the arrangement of electrons. Now, of course, it's much more simple to look at them in these Bohr diagrams. So now we've addressed the orbitals that electrons travel in pairs. Let's look at energy levels. Electrons have potential energy, and it's related to their position. So electrons farther from the nucleus have more energy. Remember, it's the force of the positive charged protons in the nucleus that draws the electrons in. So much like pulling on a rubber band, if you pull the electron away from the nucleus, it takes investment of energy. We may be able to move them to a higher energy level. We want to be careful not to confuse these energy levels, which are drawn as rings that indicate an electron's energy, with the orbitals, which have a variety of 3-dimensional shapes and indicate an electron's most likely location. Each energy level does indeed have a number of orbitals. The first energy level has only one orbital. It has just this s orbital, so it can only contain 2 electrons moving in random patterns all around the nucleus. However, when we step up to the second energy level, the L energy level, we'll see that there are 4 different orbitals. Those 4 orbitals are 1s and 3 dumbbell-shaped p orbitals, each of which contains 2 electrons. So the second energy level, L, will contain 8 electrons at its full state. And when we step up to the level M, we also see that there are 4 different orbitals, 1s and 3 p's. So it also can contain 8 different electrons. Again, oriented in 1s and 3p orbitals. Because the amount of energy an electron possesses is related to its distance from the nucleus, electrons that are the same distance from the nucleus have the same energy. Even if they occupy different orbitals, like an s or p, such electrons are said to occupy the same energy level. The energy levels are then denoted by K, L, and M, and so on. However, within biology, we won't go beyond M. So it's the filling of these orbitals to come to a maximum of 8 electrons in the second 2 shells and 2 in the inner shell that's responsible for the chemical reactivity of the elements. During some chemical reactions, electrons are transferred from one atom to another in such reactions that loss of an electron is called oxidation and gaining electron is called reduction. So in this case, we're illustrating an electron that was in the outer electron shell, outer energy level, in one of the p or s orbitals. And it is being moved from this atom over to this atom. So when we lose an electron, we become oxidized. This is what happens when metal is rusted. It's losing electrons. That oxidation you see is exactly this. Reduction is gaining the electron. So I realize that seems confusing, that gaining electron is becoming reduced, but you have to think about it in terms of the charge. Reduction means reduction in charge, as in becoming more negative by addition of an electron. We'll be addressing these redox reactions over and over as we move throughout the semester. So it's time to pull out a pen and paper and do a little diagramming. For each chapter throughout the semester, there will be a diagramming assignment, and as we go through the lectures, very often I will ask you to diagram things that will be included in the diagramming assignment. That'll give you the opportunity to check in on the discussion group and make sure that you have the right aspects included in your diagrams. So for the first part of this diagram, I would like you to diagram the element sodium using the Bohr model. That is, showing each of the electron shells or energy levels and how many electrons it takes to fill each shell. Remember, the inner shell gets 2 electrons. The second and third shells can have up to 8. And they all circulate in pairs. They're indicated in pairs here to show that they move together in one orbital, either the s or one of the p orbitals. There's no need for you to show the detail of each of the orbitals. Simply show how many electrons are in each energy level. And remember that each energy level is full when each of the 4 corresponding electron orbitals are full. So the periodic table displays elements according to the number of valence electrons. Valence electrons are the number of electrons in the outermost energy level. So that valence shell may or may not be full. If it's full, you already know it will have 8 electrons in it. This satisfies the octet rule. The octet rule defines that atoms tend to establish completely full outer energy levels. I consider that a full energy shell is like having on all your items of clothing. We'll use this analogy later when we talk about bonding. Inert or non-reactive elements have all 8 electrons in the outer shell. These are the elements that we find over here on the far right of the periodic table. They each have full electron shells. You'll notice in the arrangement of the periodic table that in the first shell there are only 2 elements, hydrogen and helium. Once that inner electron shell gets its second electron, it's full, and thus we have one of the noble gases, helium, neon, argon, so on and so forth. The second energy shell, you'll notice there are 8 different elements in that shell, each corresponding to 1 additional proton and 1 additional electron in its balanced state. So oxygen has 2 electrons in its inner shell, and then we move down to the next shell here at the second level, and we add another 6 electrons to come to an atomic number of 8 total. When we look down here at chlorine, we'll see that it has the inner energy shell full with 2 electrons. The second energy shell fills up with 8, and then we begin to fill the third energy shell. We'll notice again that there are 8 different elements, each having 1 additional proton and 1 additional electron. Now, lucky for us, we're in biology, so we will not concern ourselves with anything below the third electron shell. Aren't you glad about that? I am. So out of the 90 naturally occurring elements, only 12 of them are found in living organisms. These are the 12 elements found in living organisms. 96.3% of those are carbon, hydrogen, oxygen, and nitrogen. By far the most prevalent elements in life. They are our organic molecules, and we can call them CHON. There are some other trace elements that are very important, noted in the chart over here. Most of them are used in biological pathways. We may examine some of them in this semester, but primarily the CHON elements are of interest to us. So now for a little formative assessment. You've done your diagramming assignment, and hopefully you took the time to finish the diagram for this section of lecture. There'll be more in the next sections, but if you have any questions, feel free to get online and post to the discussion area or send me an email, get some help. It's very important that you stay ahead of this material. Let's do a color card quiz. Pull out a piece of paper. You'll simply write down the color of the answer you think is correct. Isotopes are atoms of the same element, but they differ in the number of green is electrons, yellow protons, red neutrons, and blue orbitals. Next, if a molecule gains an electron, it has been yellow oxidized, red reduced, blue electrified, or green deprotonated. Next, the atomic number of an element is determined by the number of blank. Yellow is neutrons, red is protons, blue electrons, and green energy shells. Now compare the colors of your answers with the colors on the answer key for that card quiz. Each of those were red. If you had something different, then it's time to investigate that you might be missing some information. Seek some help.